Hi, in this video we will talk about diffusion. Here on the right you see a steel gear. Steel gear should have good toughness at the core and good wear resistance at the surface, because this surface will touch another object and as time goes by it will wear. That's why we require good wear resistance at the surface. In order to achieve this, we can add more carbon, because carbon improves wear resistance, but in that case toughness will decrease if I add more carbon. So I have two opposite properties over here. In order to achieve this, first we can produce steel alloy with low carbon concentration, produce the steel gear where we will achieve good toughness throughout all material. And at second step we will create carbon rich atmosphere around steel gear, around steel gear. As we increase temperature, carbon atoms over here will have enough energy to break bonds between each other and migrate into steel. At the surface, more carbon atoms will, let's say, add up over here. When we go deeper, amount of carbon concentration will decrease. We can control this carbon concentration by controlling time. If I don't want carbon atoms to go deep into the core, I will keep time shorter. So as a result, I have more carbon at the surface, less carbon at the core. That means I will have good toughness at the core because I have less carbon over there, and I have good wear resistance at the surface because I have more carbon over here. This process is called case hardening. So we are hardening only the case, outer surface of the product. So here we use diffusion in order to change material property. So diffusion is mass transport by atomic motion. So here we transported carbon by atomic motion into steel. That is diffusion. So here you see two metals, copper and nickel bars. They are touching each other. So before diffusion, let's see atomic arrangement. So on the left I have only copper atoms, on the right only nickel atoms. You see concentration profile over here. When I am on the left, I will take it as x0 distance. When I go to the right, x goes to infinity. So when I'm on the left, concentration of copper is 100% until I reach nickel. When nickel starts, concentration of copper decreases to 0 until the end. At the same time, concentration of copper at the far right is 100% through all material. When I reach copper, it drops to 0% until the end. So we increase temperature, diffusion starts. As diffusion starts, you see orange ones are for copper. They migrated or diffused into nickel, and nickel atoms, which are gray, diffused into copper. If you analyze concentration profiles, again you see on the far left copper is 100%, but as I am going to the right, amount of copper decreases. It reach 0 when I am far away from the left. At the same time, I have the same profile here for the nickel. So when, if you look here, when copper decreases, amount of nickel increases because they diffuse into each other. So diffusion of one metal into another we call interdiffusion or impurity diffusion. The atoms move from high concentration to low concentration. Because here I have more copper, here no copper, that's why copper moves from high to low. The same applies to nickel. The diffusion happens in two mechanisms in solids. The first one is vacancy diffusion. If you see this picture over here, I have vacant position in, let's say, nickel. If enough temperature is provided, this copper will diffuse into nickel, so this copper atom will occupy this vacant position. So if you see here, the vacant position moves when atoms moves. So this is actually, if you remember, a substitutional solution. These atoms substituting vacant positions. So if I have less vacant positions, I will have a less amount of diffusion. So in order to have this kind of diffusion, I should have vacant positions. So number of vacancies are limiting factor for this kind of diffusion. That second diffusion mechanism for solids. Here you see I have a perfect crystalline structure, no vacancies. Here if you see these interstitial spaces between atoms, let's say this time this is iron and this is carbon atoms. The carbon atoms are much more smaller compared with iron. They can diffuse into interstitial spaces. So they are moving, migrating, diffusing into interstitial spaces, and that's called interstitial diffusion. Because I have unlimited amount of interstitial spaces over here, so vacancy diffusion will be more rapid. It will be faster than vacancy diffusion, because in vacancy diffusion I have limited amount of vacant positions, but for interstitial I have infinite amount of interstitial spaces. That's why this one is faster. So when we diffuse one material into another, we have to quantify how fast is this, or we have to quantify amount of diffusion or rate of diffusion. If this is G over here, this is diffusion flux. It shows rate of diffusion. Let's see. We are diffusing some material, some mass, and that mass will diffuse through certain area during specified time. That is rate of diffusion. If you look at here, diffusion flux equals the mass over area multiplied by time. If I complete, let's say, if I can diffuse 20 moles of material in 1 hour, or I can diffuse 20 moles of material in 2 hours, if you say which one will be faster, this one. That's what diffusion flux J shows, and area is also important. And how do we measure diffusion flux? that is measured empirically. So we carry out the real process, do experiment, and measure the results. In this way we can calculate it, so it's not theoretical. We have to get these values from experiment. Diffusion happens in two ways, let's say. One is non-steady state diffusion, which is dependent of time. What I want to first look to animation which will start beneath, then I will explain why do I have this non-steady state diffusion. So let's say this gray one are, let's assume the gray one are aluminium. These green atoms over here are copper. So we don't have pure material in nature. When I have aluminium, I have copper atoms as impurity inside aluminium. So these green ones are impurities inside aluminium. These green ones over here will be, so I have brought copper bar and they are touching each other, copper and aluminium touching each other. When we increase temperature, we will give enough energy to copper to break bonds. For example, if I increase temperature, this atom will have enough energy to break bonds between neighbors and diffuse into aluminium. This one over here, this is surface where the diffusion will start. The surface is x0 distance. When I go deep below the surface, x goes to infinity. Here this values 1, 1, 1. I assume that here, if you see this dashed lines over here, for this distance I have one copper atom. So concentration of copper atom is 1 for this distance. For this segment distance, amount of concentration, amount of copper is 1. So if you see throughout all material, copper is distributed uniformly as impurity. Now I will start this animation. So let's see what happens. When we increase temperature, diffusion starts. So 5 copper atoms diffused into closest distance. Here I have 5 more, in total 6 atoms. Sorry, before, if you see these dashed lines here, in the upper graph, again I have distance x in vertical axis. In y-axis I have concentration. This will show amount of copper through material. So this dashed line shows that through all material, concentration of copper is 1. Now when diffusion starts, you see at the surface here, when x is 0, diffusion peaked to 6, and when I go deeper into the material, the amount of copper is still 1. We will continue the process. Now you see this graph, at the surface I have 6 atoms. At position over here I have 2, and the rest of the material 1. Again at the surface 6, 3 in this distance, 2 here, 1 for the rest of the material. The same thing, and that's it. So what we see over here, when diffusion starts or happens, at the surface I will have maximum amount of concentration. When I go deeper below the surface, concentration of diffused copper decreases, as you can see from this graph again. So what I want to do, the concentration of copper changes when you analyze these distances over here. This is X, increases in this way. As I move in position to the right, amount of copper or diffusing species, so copper here is diffusing species. When I move in position, amount of copper decreases, changes. So concentration here is a function of position, because when I change position, concentration change, as you can see over here, 6, 5, 4, 3, 2, and etc. And plus, let me return over here. So here, time is going. As time goes, you see concentration, you see this table over here. As time goes, these values change. When I stop the time, measure concentration, you see it is 6, 3, 2, 1. When I continue with time, stop and measure, concentration has changed. So concentration changes with time. So here, concentration changes with position and time when it depends on time. That is non-steady state diffusion. And that's it. So here, steady state diffusion. In steady state diffusion, diffusion rate is independent of time. What I mean is, time doesn't affect concentration of diffusing species. But first, watch the animation, because I have some tricky part over here. So again, I have X distance goes to infinity when I move in this direction. The same X-axis, this vertical line is for carbon concentration. Here, again, I have green ones are impurity copper in aluminium. So here you see this green ones. This is not empty actually. I have aluminium atoms over there, but I didn't draw them to make things simple. So let's start. If you see, concentration changes. At the surface I have maximum concentration. Again, at the surface when X is 0, I have maximum concentration, and when I go deep below the surface, it is 1. It didn't change. When time goes by, you see how concentration changes. I have more and more atoms accumulated below the surface, and you can see the graph. That is for time. That's for different time. Let's say after 1 hour, this red one. After 2 hours, you will see this blue one. So for this distance over here, before it was 1, after some time it was 2. If I wait some more, let's say 3 more hours, concentration will be 3, and so on. So until that point, concentration of diffusing species, in this case copper, changes with position and with time. If you see, when I move in position to the right, you see how concentration change. So concentration is function of position, and plus, so far you see that when time goes, if you see that that's time going, you see changing concentrations over here. This concentration is a function of time also, until some time. Now if you see this straight line over here, when you have steady state diffusion, what we do is we create same pressure, equal pressure at both sides of this aluminum bar, let's say. When I have a high amount of let's say copper over here, high amount of copper, you see low amount of copper over here. It's because I have high concentration here, low at the other end. Diffusion starts because of concentration difference, and when we increase temperature, again this copper atom will have enough energy to break bonds between neighbors and diffuse into aluminum. And when that happens, let me erase all of this. When that happens, diffusion starts, but first it is non-steady until it reaches balance. So you see diffusion changes with time until we achieve this straight line over here. So that's the point diffusion becomes steady. It starts as non-steady but reaches a steady point where I have this straight line. What will happen if I continue this process? If you see, whatever comes in goes out. This atom doesn't stay inside. It doesn't. Concentration does not increase. So a question: does concentration change with time? The answer will be no, because you see these values don't change, because they come in and go out. They don't stay inside. That's why these values don't change. So, but these values change when I move in position. You see, when I go from left to the right, you see this concentration drops. So in steady state diffusion, concentration is a function of position, but it is not dependent on time. It is independent, because as you see in the animation, so right now time is counting, and you see that concentration doesn't change with time. I hope that was clear. So where we can use this, so what's the application for this? We can in industry they purify hydrogen gas through this process. So they have a palladium sheet, a thin palladium sheet. They have a hydrogen gas, it will have some impurity, it is mixed with other gases, and this palladium sheet only allows hydrogen through it. So as the impurity stays on left side, so what comes in goes out. They use steady state diffusion to purify hydrogen gas. Next, that's the line which we did achieve over here, this line over here. So I have at distance 1, I have a certain concentration of diffusing species. At different position, another one. But if you see, it goes down. That is a surface, it is deep into the material. When we go deep into the material, concentration drops. And that's the direction of diffusion, from high concentration to low concentration. In steady state diffusion, that is our equation over here, it's called Fick's first law of diffusion. This one is diffusion flux. This is a diffusion coefficient, as it's written over here. It shows how fast diffusion will be, and in order to determine diffusion coefficient, we have to know which material diffuses into another. So in previous picture, copper was diffusing into aluminum at certain temperature. So all these three defines diffusion coefficient, and we will discuss it in details in further slides. So here diffusion coefficient is here. Now this one means difference in concentration divided by difference in position. We can open this up as this: C2 minus C1 over X2 minus X1. What's the difference between these signs? This is differential form. This is differential form. It means really small difference, near zero. And this is delta, which we usually use. When our line is straight, we assume that it is straight, and we can use this delta and open it up like this. And this is also called, this ratio over here is called concentration gradient. And concentration gradient is driving force for steady state diffusion. That's why diffusion happens, because this change difference in concentration. Let's do some example. So we have a plate of iron. At one side we have carbon rich atmosphere, on another side carbon deficient atmosphere. We will decrease temperature to 700 degrees Celsius. If we achieve steady state condition, we have to find diffusion flux J. If says that that is surface where x is 0, below surface, below 5 millimeters below the surface, I have this area. It says that carbon concentration at that part of the plate will be 1.2. At 10 millimeters into the surface, into the material, carbon concentration is this. Diffusion coefficient is given. If it is not, we can read it from the table. We will see it later. So we have to calculate diffusion flux. It says that it is steady state diffusion. So I will use this equation. If I open it up, it will be C2 minus C1, X2 minus X1. So this is X1, X2, C1, C2. So let's put everything in place. But first, if you see diffusion coefficient, its unit is square meters per second. For concentration, it is kilograms per cubic meters. But these distances are in millimeters. We have to change millimeters to meters. In order to do this, if I multiply by this, I will convert millimeters to meters. So negative 3 multiplied by this, C2 0.8 minus 1.2 kilograms per cubic meters over X2 is 10 minus 5, 10 to the power of 3 meters. So if we do calculate this, it will be multiplied by negative 0.4 over 5 and 4 units. So negatives will be gone. So let me simplify this. So our final answer is 2.4 10 to the power of negative 9 kilograms per square meter multiplied by second. That is diffusion flux for these conditions. Now for non-steady state diffusion, keep in mind that it changes with position and time. So we have different kind of equation which we call Fick's second law. But don't be afraid, we will apply some boundary conditions to this equation and it will be much more manageable for us. So first, let's do some introductions. So here we have aluminium bar, gray one. In aluminium bar I have orange atoms, which is copper. These are impurity atoms inside aluminium. So it was there before diffusion. We call So this, if you measure these atoms over here, which was before diffusion as an impurity, we will call this C0, initial concentration of copper or pre-existing concentration of copper in aluminium. Again, this is surface where x will be 0. When we go below the surface deeper, x goes toward infinity. Here we bring copper bar and they touch each other, and this inside this copper I have certain amount of copper surface, certain concentration of copper. We call this CS, surface concentration of copper atoms. So around this atmosphere I bring copper rich atmosphere. That amount is CS, surface concentration. So before diffusion starts, when time is 0, so before diffusion, what will be amount of copper through all material from 0 to infinity? So through all material before diffusion, amount of copper will be equal to previous one, C0. So concentration equals to C0 to initial amount of copper atoms through all material, because I don't have diffusion yet. After diffusion starts, so time starts ticking. After diffusion starts, at the surface over here, when x is 0, so at the surface concentration of copper will be equal to whatever I have over here, CS. So at the surface, when concentration starts, when diffusion starts, concentration equals to CS. If you see over here in this graph, that is x0. When diffusion starts, at the surface, concentration equals to this 0, and concentration is CS at the start. And when I go deeper into the material, so when copper starts to diffuse into material, it cannot go deeper. So I have more copper diffusing here, less and less. And when I go too deep, when I go to infinity, diffusing atoms will not reach this part. That's why amount of copper when I'm going toward far right to infinity will be equal to previous one, to initial concentration of copper. That wants to say us that diffusing species, in this case copper, cannot reach deep below the surface. So that's our assumptions, that's our boundary conditions. When we apply these conditions, equation will simplify to this one over here. So what do I have here? This one is C0, initial concentration of diffusing species. I will use copper for diffusing species, so it's easier for me to say. So that is initial amount of copper, surface concentration of copper. So here, if you say this CXT, when copper diffuses into aluminium, below the surface at certain distance, at certain time, we can measure concentration of copper. So if you see, let's return to your previous picture over here. So here I had CS. If you see this value over here, 1.2, 0.8, this one 1.2 is carbon concentration at 5 millimeter distance, equals to 1.2. That's instead of x, I add 5. This one over here is concentration of let's say here it was on. So it's concentration of copper at 10 millimeter distance into the host metal, which is 0.8. So that's instead of x. I have the same thing over here. So that is x0, surface, that is goes to infinity. So at some distance into the material, let's say when x is 2 millimeters below the surface, after I have 1 hour diffusion, I'm here, I can measure concentration of copper. I have some value over here. If I wait more after 2 hours, if I measure, I will get some other concentration. If I wait 3 hours, I'll have this another concentration. So for certain position, for certain time, we can measure concentration of diffusing species inside material, and that's it. This X, that's the same X over here. So if I'm trying to measure 5 millimeters below the surface, I will plug in 5 millimeter over here. Diffusion coefficient, we can read it from the table or calculate it ourselves. It depends on diffusing species, host metal, and temperature, and that is time of diffusion. And this one over here is error Gaussian error function, which opens up like this. So here, instead of x over 2 dt, we will say that this is equals to z. So error function z equals to some value to this equation over here. Instead of doing this complicated integral, we are given ready calculated values from the table. So instead of doing this calculation, you can read values from this table. Let's move it. So I have 3 columns. That's what I have. Again, let me write. This is z. So that means, let's say, take these values. If x over 2 dt equals to 0.05, I have error function 0.05. If I plug in this value, I will get this one, 0.0564. So that's the way how we use this table. So next, we will solve some example and see how do we use these tables and equations. We have non-steady state diffusion. Pay attention and read this problem. It doesn't state that we have steady state diffusion. If it is steady state, it mentions it specifically. So here I have a alloy. Initially has a uniform carbon concentration 0.25. So initial word tells me that this is C0. It will be treated at this temperature if the concentration of carbon at the surface is suddenly brought and maintained at this. So it says surface, so that's keyword. Surface concentration will be this. How long will it take? We are searching for time to achieve carbon content this at a position 0.5 millimeters below the surface. So when x is 0.5, we want to achieve 0.80 weight percentage of carbon. So when we are deep 0.5 millimeters below the surface, carbon content should be this. It asks how long will it take. Let me try to draw it. That's x0. Here carbon concentration is equal to surface concentration. When x is 0.5, this concentration is 0.8, and before diffusion through all material, carbon concentration was 0.25. Diffusion coefficient, which is D for carbon in iron at this temperature. So if you remember, diffusion coefficient is defined by diffusing species, host metal, and temperature. So here I have carbon in iron at 950 degrees Celsius. Instead of reading from table, it is given to us for now. It says the diffusion coefficient is this. So let's start with calculations. First, let me clean up some space. So our equation was this. cx minus c0 over this equals if I just replace values, it will be 0.8 minus 0.25 over and error function will be equal sorry. So, and if I calculate this, the value will be 0.4211. Pay attention to take at least 4 digits, not less. Now we have found out that error function, remember we say that this will be equal to z. Let me simplify it. So error function z equals to this. Now I will go to table and try to find that when z is what, my answer will be this. So here I will erase everything on this slide. Okay. So my value is error function z equals to 0.4211. Now let's search. I will be looking here, searching for this value. I see that I don't have exact value. If you see this one over here, one is below 0.4211 and one is bigger, and that is z values for them. So my value I am searching is in between here, but what it will be, let's draw this. If this is z axis and this is error function z, when z is 0.35, and when z is 0.40, so one value is here, another one here. I am looking to very small distance. It will be linear line, and error function z value, mine is this, somewhere in between. So here from this line I am searching for the z value. If you see that's a line, 2 points are given, I am searching for this one. From here I think you can guess the way how you can reach this value. We will use interpolation. If I write this down over here, when z is 0.35, the z I am searching for, it will be 4211, and when z is 40, it is 4284. So what I will do, this difference in this, z minus 0.05 over difference in this, equals to difference in this over difference in this. So from here I will calculate z, which is equal to, z is 0.39. 2 digits is enough. So as you can see, it is in between these two values. So I found out Z. Now let's continue. I don't have space over here. So Z is 0.39, and if you remember, we named this one Z. I will write down T equals something. That's why square everything. X squared over 4dt equals Z squared, and time will be equal to X squared over 4dz squared. Now replace values. X was 0.5 millimeters, converted to meters over 4. Diffusion coefficient is 1.6 over 10 to the negative 11 square meters per second. So if this is a meter over here, that's why I'm converting here. Multiplied by Z squared. Now carry out the calculation. The value is 25,682 seconds, because if it is a second here, meter squared will be gone, and divide by 3600, it is 7 hours. That means it will take us 7 hours to reach this carbon concentration below 0.5 millimeter to the surface. So initial concentration was 0.25. We increased from this to this in 7 hours. That's how slow diffusion process is. Next, in this example, what we have aluminium bar. Copper is diffusing into aluminium, so they are touching each other. So for metals, they touch each other. For gases, it will be around it. So copper touches aluminium. Diffusion coefficients for copper are given. But first, pause and read it. I will summarize it in different way. So what we need to do says that copper is diffusing into aluminium at 600 degrees Celsius temperature, where diffusion coefficient defined by these three factors will be this. And it says that when I do this, at certain x distance below the surface, we will reach to a certain amount of copper concentration. When I do this process in this way, now it says that again I'm diffusing copper into aluminium, but at different temperature, because temperature changes, every condition is same, only difference is temperature. So temperature change, that's why diffusion coefficient drops to this. Now it says that I am changing temperature, but I want to achieve same concentration of copper at the same distance below the surface. So it says for this first process it took 10 hours to do it. How long will it take if I decrease temperature? That's our problem is. So let's see, but remember, metals are same. Host metal diffusion species are same, so conditions are same. CS and C0 will be same, X is same, CX is same. So it says that I want to reach same. These are same, so these are constant. Let me write the equation. So let's see. We want to achieve same CX at same position. Conditions are same. This none are changing. So what change is only this diffusion over here, because I decreased the temperature. So if I want to get the same CX value, my aim is to get the same CX value. If I keep this constant, if I do this all these calculations and carry out procedure, I can achieve the same Cx value. So diffusion coefficient for 600 degrees Celsius multiplied by time for same temperature equals to diffusion coefficient for different temperature and time for this. So what I mean is, if I have certain value over here, plug in over here, do calculations, and you reach some Cx. If I have some other equal value, if I plug in over here, I will get the same Cx. That's why I want to keep them equal to each other. So these values are given. I need to find this time. The time for 500 will be equal to diffusion 600 times 600 over diffusion 500. So plug in. Diffusion for 600 degrees Celsius is 5.3 multiplied by this, multiplied by time is 10 hours. Over 4.8, 14. So it will be 110 hours. So what they have, when we decrease temperature by 100 degrees Celsius, it takes 11 times more time to get the same concentration at certain distance. So in this slide, what we have, you see diffusing species over here, host metal. So let's say if copper diffusing into alpha iron, here copper is diffusing species, alpha iron is host metal. These two values will define this D0. D0 is exponential. This one is pre-exponential and depends on diffusing materials. So this value over here defined by these two, diffusing species and host metal. It shows how well these two are capable to diffuse into each other. I have this activation energy QD over here. It is given in two different units. I will mainly use this one, and in the book we mainly use this one. So this value, what is this activation energy? In order for carbon atom to break bonds between neighbor atoms and diffuse into iron, it needs some energy to do this, to break that bond and move. That is this energy over here, activation energy. I need 80 kilojoules per mole to move carbon atoms into alpha iron. And again, activation energy depends on these two. So D0 and QD depends on diffusing species and host metal. It doesn't depend on temperature. So temperature doesn't affect these two. Now we have some temperatures listed, and for each temperature I have diffusion coefficients given. So what do I have? Let's see, let's erase everything. When we have iron diffusing in alpha iron for 500 degrees Celsius, that is diffusion coefficient. Now this time, if copper is diffusing in alpha iron, the same metal, at the same temperature, I have different diffusion coefficient. This one will be bigger. That means a diffusing species and host metal defines diffusion, and temperature defines diffusion coefficient. When we change diffusing species, diffusion coefficient changes, and alpha iron will be substitutional diffusion. It will be vacancy diffusion. They substitute each other, and carbon in iron will be interstitial diffusion. And if you remember, vacancy diffusion is faster than interstitial diffusion, as it can be seen here. This diffusion coefficient is bigger than this one. It is faster. It will take less time to achieve the process. And next, again, let's see, for carbon in iron at 500 degrees Celsius, it takes this amount of, let's say, diffusion coefficient. With the increased temperature for the same element, you can see that diffusion coefficient got even bigger. It increased again. That means when we change temperature, diffusion coefficient increases. So diffusion coefficient is defined by diffusing species, host metal, and temperature. And temperature is extremely important. If you see this in previous example, when we decrease the temperature by 100 degrees Celsius, it took us 11 times more time. That's how temperature is important. So here, I think I have mentioned everything. So let's move on. So far, diffusion coefficient were given to us from this table over here. But if it's not given, for example, I have 500 and 900 here, but if it is 600, we can calculate it by equation, by this equation. So that's diffusion coefficient, pre-exponential, and activation energy, which depends on diffusing species and host material. Gas constant, it is a constant value. Over here it's joules per moles multiplied by Kelvin. That's why if you see joules per moles over here, that's why in this table I will choose activation energy in kilojoules per mole, because that's somehow the same unit. And temperature is in kelvins, so we will have to convert Celsius to Kelvin. So if I add 273, we will convert Celsius to Kelvin. And this exponential over here is for this E value, which is 2.71. In order to make it easier to write in a line, we use this exponential instead of Y. That's the same thing. And let's continue. Now we have to compute diffusion coefficient for magnesium in aluminum. So we are diffusing magnesium in aluminum at 500 degrees Celsius. So let's go to the table. Magnesium in aluminum. Here, magnesium is diffusing into aluminum, but I have only 500 degrees listed here. That's why I will have to calculate it. But before, let's take these values, D0 and activation energy of a calculation. So for magnesium in aluminum, D0 is this, and activation energy is this, kilojoules per mole. Now our equation was D equals D0 E to the power of negative activation energy all over gas constant. I'm just inserting values multiplied by temperature, and for that temperature I have to convert this to Kelvin. It will be 3 to So here this kelvins will be gone, but here it's kilojoule and this one is joule. That's why I have to do something over here. It will be 131,000 joules per mole. So these joules will be gone, moles will be gone. For D0, I forgot to replace this value 1.2. here to the power of negative, let's calculate this one. It will be negative 19.15, and the final here to the power final value is 1.79 multiplied by this square meters per second. So that's diffusion coefficient for magnesium in aluminum at 550 degrees Celsius. So for summary, diffusion faster for open crystal structures and slower for close packed structures. So why? In order to diffusion happen, this diffusion species should go through the material. If these are open, let's say I will have, let's see, this is open structure, let's say, and this one is close packed structure. So if in open crystal structure I have this empty space to move through, so I will have faster diffusion. In close packed structure, let's say it's not exact, but it's hard to move through close packed structure, so diffusion will be slower. Materials with secondary bonding, secondary bondings are weak bonds. That's why it will be easier to break that bonds and diffuse. And covalent bonds are strong bonds. That's why it will be difficult to break that bond and diffuse. That's why this one will be slower and this one faster. Smaller diffusing atoms. So if atoms are smaller, as in this picture over here, this because it's smaller, it can move freely. It will be more mobile to move through because its size. And if it is larger, again, this larger atoms will be difficult to move through this one. Again, this picture is not exact. So we have these atoms, elements. I have some vacancies. As this vibrate, at certain time vacancy will move to this one over here. It will be vacant position, and this atom will be able to go there using vacancies, and vacancies are limited, so smaller diffusion rate. Large density materials and high density materials. So again, if the density is lower, so that means material atoms are far away from each other, it will be easier to move between them, and the opposite for high density materials. That's it for today.